Hello. So in today's lecture, we're going to be looking at the axioms of quantum mechanics. Okay, so these are the initial things that we need to get out of the way before we can do quantum mechanics properly. Okay, in the next lecture, we will be looking at the Schrödinger equation, how to solve it for a given system, and what we can do with that. Okay, but first the axioms. So axiom number one. Okay, so this first axiom describes the state of a quantum system and where these states live. Okay, so for every quantum system, okay, so that's in general quantum system, whether it be one particle, a few particles, and so on. We have that for every quantum system. There is a Hilbert space, a complex separable Hilbert space. Okay, we call that H. Okay, so for every quantum system, there's a separable Hilbert space H. We'll get to what a Hilbert space is shortly, but it's just a vector space. Okay, the states of the quantum system. The states of the quantum system are represented by vectors in this Hilbert space. Okay, so you may be familiar with the idea of configuration space or phase space for a classical system. So in classical mechanics, the state of a system can be described by the positions of the particles and their momenta. So if you know that, you know all the information about the system and how the system will evolve in time. In quantum mechanics, it's a similar idea. We have a space of possible states, but instead of using a configuration space or a phase space, we use this vector space H. Okay, and then the elements of this vector space will describe the system, okay, in whatever state it may be in. Okay, so we need to go over what a Hilbert space is and what a separable Hilbert space is. Okay, so let's just start off with what a Hilbert space is. So, definition. A Hilbert space, okay, usually given by H, is a vector space with an inner product. Okay, there is an extra condition of completeness, but we won't be getting into that. Okay, for our purposes, just knowing that the Hilbert space is a vector space with an inner product, that is as far into this as we're going to go. Okay, and we know what a vector space is, we know what an inner product is, so now we know what a Hilbert space is. Okay, but then there's this extra word, separable. What does that mean? Okay, so definition. A Hilbert space H is called separable if, and then there's a condition, if it has a basis that is, okay, so we've got a basis that is A, countable, okay, which means we can label the elements of the basis like 1, 2, 3, ... Okay, so it may be infinite, it may be finite, but either way, it has to be countable. And B, it can be orthonormal. And if it is not orthonormal, then it can be made into an orthonormal basis. Okay, but this basis needs to exist. So orthonormal. Okay, just a reminder on what orthonormal means. It means that for all E1 and E2 in the basis, okay, it's called the basis B, we have that the inner product of E1 with E2 is delta 1, 2. So it's 1 if those elements are the same, and it's 0 if they are different. Okay, so that is the orthonormal part. Okay, orthogonal and normalized. Okay, so now we know what this complex separable Hilbert space means. So complex, the underlying field is the set of complex numbers. Separable, we know that it has the Hilbert space is a vector space. It has a countable basis, and the basis is orthonormal with respect to that inner product. Okay, so the inner product on the vector space turns it into a Hilbert space. Okay, so that is the first axiom on the system and how we describe the system. The second axiom has to do with the observables of the system, so the things that we can measure. Axiom 2. The observables, yeah, those are the things that we can measure, are self-adjoints. Yeah, we know what that means now. Linear maps. Yeah, we can write that as A for the linear map. And this goes from the Hilbert space into the Hilbert space. Okay, so those are the observables. So things that you can observe, such as position. In classical mechanics, we just have the variable x for position. Here, that gets translated into a linear map. And if you have something like the momentum, that becomes a linear map. The energy, that becomes a linear map. Yeah, so anything that you can measure in the classical system now becomes a self-adjoint linear map for the quantum system. Okay, so now that we know what the observables are, how do we measure them? Okay, so that brings us to axiom 3. Okay, so let's say we have an observable A. So let A be an observable, or in this case, we know it's a self-adjoint linear map. So let A be an observable of the quantum system. Okay, so the possible measurement results, if we were to measure A, are the eigenvalues of A. So the possible measurement results are the eigenvalues of A. Okay, so you can't just measure anything. The measurement results has to be an eigenvalue of the observable. Okay, so there's this restriction on what can be measured. Okay, now you may have heard that quantum mechanics is probabilistic. So when you are measuring something, you're not guaranteed to get a certain value. So if you were measuring the position of something, that specific position may not be measured. You have a range of possible measurement values, and each measurement value has a certain probability to it. Okay, so let AK be the eigenvalues of A. Okay, so we know that that means this A sub K, that is a possible measurement value. So let AK be the eigenvalues of A, and let K, okay, so this subscript K, that runs over some indexing range to account for the different eigenvalues. And then we have the associated eigenvectors for the different K values. Let K be the corresponding eigenvalue. Eigenvector, sorry. Okay. Then the probability of measuring AK is given by P is equal to the absolute value of this inner product of psi with K, where psi is the initial state of the system, and K is the eigenvector corresponding to that particular measurement result. So you can go through all of the possible measurement results. So those are all the possible AKs. You take this inner product and you square the result, and that gives you the probability of measuring that result. And if you add up all the probabilities, you'll get 1. Okay, because you have to get one of those values after measurement. So where psi is the state of the system, or state vector of the system, before measurement. Okay. Then after measurement, the state of the system changes from being psi to being K, which is what you corresponding to the eigenvalue that you measured. So if a K is measured, okay, because you're going to get some value. So if that value is AK, so if AK is the value measured, then the new state of the system is the K vector. Okay, so the eigenvector corresponding to that eigenvalue AK. And we call this projective dynamics because we started out in the state psi, which may have been some linear combination of states, some arbitrary states in the Hilbert space. And then after measurement, we are definitely in this new state, K. Okay, so we project onto that state. Okay, so this is called projective dynamics. Because the state is projected onto that eigenvector. Okay, so you end up with something, with a vector that is along that line. And of course, it has to be normalized. Okay, so this projective dynamics can be written in a different way. Okay, so we could write this as, okay, so this process can be written as the new state after measurement is pk acting on SAR, and then that's going to give us a new state. But remember, the states have to be normalized, so we have to divide by the inner product of SAR with the projected state. Okay. Where this pk is a projection operator. So if you took a look at those exercises on vector spaces and operators or linear maps, there were a couple exercises on projectors. Okay, so where pk is the projector onto the k state. Okay. So this takes the input SAR and it projects it onto the k vector. Okay, so if that's a bit confusing, take a look at the exercise. And if that doesn't help, please email me if you have any issues with this. Okay, so this is called the projective dynamics. We've got the state SAR, and it gets projected with the projection operator onto the new state after the measurement. Okay, so this axiom deals with what happens during a measurement. The last axiom deals with what happens in between measurements. Okay, so axiom 4. Okay, during the time interval from T1 to T2 with no measurement, okay, because measurement is discussed in the previous axiom, so this one is with no measurement. Okay. The system follows unitary dynamics. Okay, so when there's a measurement, we have projective dynamics. When there is no measurement, we have unitary dynamics. Okay, so how does this work? Well, the state SAR prime is given by a unitary map that depends on T1 and T2, acting on the initial state SAR. Okay, so if you want to know what the state of the system is after this time interval, you take the initial state, you act on it with the unitary dynamics operator, and that gives you the new state. Okay, so we know that this is unitary, which means that U dagger is the identity. Okay, so that's just since we know that it's unitary. Okay, so what exactly is this operator? Okay, so I'm just going to write it down now. We will see where this actually comes from in the next lecture. Okay, so U of T1, T2 is equal to e to the minus r T2 minus T1 over h bar times h, where h is the Hamiltonian operator or the energy operator. Okay, so that is the self-adjoint linear map corresponding to the energy observable. So h is the Hamiltonian, okay, or the self-adjoint energy observable. Okay, so this is the energy observable. Okay, and since it's an observable, we know it's self-adjoint, and everything that goes with being self-adjoint, which we discussed on the section on Hermitian matrices. Okay, and we know that all unitary operators can be written as e to the r h for some self-adjoint or Hermitian operator h. Okay, so we see that over here. Okay, we've got some unitary operator we want to define, and we know that we can define it using a self-adjoint linear operator. Okay. In this case, for the time evolution or this unitary dynamics, that's given by the Hamiltonian. Okay, but we will see explicitly how we get this in the following lecture. Okay, so that's it for today. If you have any questions on these axioms or anything in particular here, so we did go through, let's go back here, complex vector spaces. We've gone through inner products, bases, orthonormal bases, self-adjointness we've covered, projectors, and unitary operators. So we have covered that before, but if you're still unsure about any of those terms and how we use them, please send me an email or you can visit me in my office. All the details are available on the course webpage. Okay, and please take note of the due dates for the tutorials and the assignment. Okay, so remember that is Monday. So the assignment is due 9 a.m. on Monday, and the tutorial from this week, that is due at 5 p.m. Okay, so please make sure you submit those on time. Okay, but if you have any questions, please let me know. Yeah, I'll see you next time.